Welcome to the AI Research Roundup. I'm Alex. Today we're looking at a paper from the Hugging Face trending list, published on February 13th, 2026, just 6 days ago. It introduces a new method that achieves 97% attention sparsity and delivers an 18.6 times speedup on video diffusion models, all while preserving generation quality. The paper is titled SLA2, Sparse Linear Attention with Learnable Routing and QAT, and as we'll see later, these efficiency gains are quite significant for the future of high-resolution video generation. And for those interested in the implementation, the authors have shared their code on GitHub. Alright, Figure 1 illustrates the overall pipeline of the SLA2 method. On the left, we have the standard query, key, and value inputs, but notice the orange block labeled Learnable Router in the center. This router analyzes the queries and keys to generate a mask, M, which dynamically selects the most critical attention pairs. Following the top path, the model uses this mask to perform sparse attention, computing exact softmax values only for those selected elements to get the sparse output, OS. Meanwhile, the bottom path processes the global context using efficient linear attention to generate the linear output, OL. To combine them, the system uses a learnable parameter, alpha, to weight and sum the two branches, ensuring the final output balances precision and efficiency. So, having seen the architecture, Table 1 provides the hard numbers comparing SLA2 against baselines like versus MoBA and versus SA. The evaluation covers two model sizes, the WAN 2.1 1.3 billion and 14 billion parameter versions. If you look at the quality columns in the center, which measure factors like imaging quality and aesthetic quality, SLA2 consistently scores the highest among the sparse methods. Most impressively, in the bottom rows for each model, the method reaches 97% sparsity. This drastically cuts the computational cost, measured here in floating point operations, while preserving generation quality that rivals the full attention baseline. While Table 1 gave us the numbers, Figure 2 shows what this actually looks like in generated video frames using the WAN 2.1 1.3 billion model. The top left panel displays the full attention baseline, which serves as our ground truth. Comparing that to the top right panel, showing SLA2 at 97% sparsity, the visual fidelity is remarkably similar. This confirms that the method preserves fine details even when skipping most attention calculations, whereas the baselines in the lower rows often struggle to maintain this consistency. Well, shifting focus to efficiency, Figure 4 compares the forward kernel speed across different attention mechanisms. The vertical axis measures throughput in trillion operations per second, or TOPS. Starting on the far left, the gray bar shows flash attention lagging behind at roughly 200 TOPS. In the middle, competing sparse methods like versus MoBA and versus SA show gains, climbing up to 1500 TOPS. However, SLA2 dominates on the far right. The tall purple bar for 97% sparsity hits over 4000 TOPS, which is an 18-fold improvement over the standard baseline. Okay, while kernel speed is important, Figure 5 reveals the impact on actual user wait times. These charts split latency into two parts, the orange segments for attention and the green for other operations. In the top panel for the 1.3 billion parameter model, SLA2 shrinks the attention time from 97 seconds to just 7, driving a 2.3 times total speedup. The gains are even starker in the bottom panel for the 14 billion parameter model, where attention originally dominated at 2500 seconds. SLA2 cuts this to roughly 200, resulting in a 4.35 times faster generation. So, having established the speed benefits, Table 2 breaks down why the specific components of SLA2 matter. The middle rows compare the full method against versions without quantization-aware training, and with the older TopK router. We see that removing QAT causes a drop in aesthetic quality, confirming that the training strategy is essential. Finally, the bottom section shows that even when pushing sparsity to 97%, the imaging quality holds steady at 66.6, proving the method remains robust. Wrapping up, SLA2 proves that we can accelerate video diffusion models by over 18 times just by routing attention more intelligently. The combination of a learnable router and quantization-aware training allows for 97% sparsity without degrading the final video quality. That's it for this episode of the AI Research Roundup. I'm Alex. Thanks for listening.